Okay, welcome everyone to the second half of the Oxford Discrete Mathematics and Probability seminar this morning. So as usual, we have everyone other than the speaker muted, and please do ask questions in the chat if you have questions, and then either we'll interrupt Anita if it's a question that needs answering. It's good to answer immediately, otherwise we'll wait till the end of the talk. So it's a great pleasure to have Anita Liebenau talking this morning. Great that we can have speakers from the other side of the world. So I'll hand over with no further ado.
Well, thanks, Alex. And thanks also, Christina, who can't be here, for inviting me to speak here. It's a great pleasure. So I want to talk about the threshold bias of the clique-factor game, which is a joint work with Raiko and Nenadov. From when we were both, well, it started initially when we were both postdocs at Monash, but he's now in Zurich with Google Research. And so to tell you about the threshold bias of the clique-factor games, there are three things in the title that I should tell you. So what is a clique-factor? Which game am I talking about? And then what's the threshold bias? So let me start right away with telling you what a clique-factor is. So a clique-factor for me for this talk is just a collection of n over r vertex-disjoint copies of Kr. So there's the copies of Kr, vertex-disjoint, they span everything, the whole vertex set. And the thing that I want you to keep in mind for the rest of this talk is that they're spanning, that every vertex is contained in a triangle, but also that r here is really a constant and n is typically very large. So that's kind of the setup for the talk. Now, what game am I talking about here? So that the games I have in mind are maker-breaker games. Now, for those who have never seen those, let me explain you the rules, the standard rules of the maker-breaker games. The maker-breaker game always comes with a set X, which is called the board, and a family of subsets F, which is called a family of winning sets. And then in a round, the game is played in rounds, and in one round, maker claims one element, which is previously unclaimed. So say she colors it red, and then breaker plays with a bias. So I'm calling this B bias maker-breaker games. Breaker claims B, previously unclaimed elements of X. And then this is a game, so we want to know who is the winner. Now, in maker is declared the winner of a particular play of the game if maker manages to occupy all elements of some of these winning sets, F and F. And otherwise, breaker wins. So these are like the standard rules. Now, let me give you some very simple examples. So for the whole talk, the board X will always be the edge set of the complete graph on n vertices. Nothing else will happen in this talk. And then a family of winning sets, for example, can be the set of all triangles. So what's then the game? The game is maker tries to occupy a copy of a triangle, and breaker tries to prevent this. So breaker's aim is that maker does not obtain a triangle. So these two goals are opposing, so you always have exactly one player who wins the game. And from now on, what I should say is that this is a perfect information game. So in theory, you know what your opponent will do if you do this or that move. So one player always has a winning strategy, okay, for a given n and b. So from now on, when I say maker wins the game, I mean that maker has a winning strategy, and same that breaker wins if breaker has a winning strategy. Now, other examples are when I have the family of all perfect matchings on the edge set of Kn. So in this case, maker tries to occupy a perfect matching, and breaker tries to prevent this. Or I could have another classical example is when F is the family of all spanning trees. So in that case, maker tries to obtain a spanning subgraph that is connected. Okay, so this game is also called the connectivity game. And the fourth of the classical examples that I will mention here is the Hamilton cycles. So when maker tries to obtain a Hamilton cycle in Kn. Now, all of these games have something in common, namely that if a breaker plays with bias 1, then maker has a really easy winning strategy. So for the triangles, you can think for yourself what would be a simple winning strategy if you play on, say, 6 vertices, a simple strategy for maker to obtain a triangle. Okay, and the other games, for those you have to work a little bit, but for those, there also exist winning strategies for maker, where maker wins within almost an optimal number of moves. So that's what I mean, maker wins easily. So what has been suggested by Fratal and Erdős in 1978 is to introduce a bias to give some advantage to breaker. So that's why breaker is allowed in a round to occupy up to B elements. And then we can ask, well, how large do I have to make this B so that the game turns from a maker win to a breaker win? Okay, that's called the threshold bias, and it's denoted by B star. And for this talk, I'll just say the threshold bias is the smallest B such that breaker wins the B biased game XF. Okay, and this is well defined unless your family of winning sets is somewhat stupid. So if your F should be non-empty and your winning sets should have size at least 2, otherwise it's a trivial maker win, whatever B is. Okay, right, and then these games are what's called bias monotone. So if I have for some B that maker wins for that bias, then if some B prime is less than B, then maker still can use the same winning strategy. So if maker wins for some B, it wins for all smaller B primes. Because like these additional edges that you would occupy as maker never harm you in claiming some winning set. Right? More elements never harm you. And the same for breaker. If for some B I manage to prove that breaker has a winning strategy, then for every larger B, breaker has a winning strategy, just using the same strategy and putting like 1 breaker mark in every single one of these winning sets. So that's a threshold bias, and that's a very central topic in positional games. So let me tell you what's known about the threshold bias for these natural games. So the threshold bias for these 3 spanning games, the connectivity game, the perfect matching game, and the Hamiltonicity game, is always asymptotically equal to n over log n. And this goes back to the paper I mentioned already due to Fratal and Erdős. So they proved for each of these 3 spanning games that they proved that if the bias is 1 plus epsilon times n over log n, then breaker has a winning strategy. And the winning strategy for breaker really is just isolating a vertex. So that's all they did. So when B is of the order 1 plus epsilon, when B is 1 plus epsilon times n over log n, breaker can isolate a vertex. So in these 3 spanning games, breaker wins. And then the other results are like consecutively getting maker's bias up there. So proving strategies for maker for larger and larger bias until eventually, well, people could prove the 1 plus little of 1 is the correct constant. So that's a famous result for the connectivity game is due to Gebauer and Szabo. And for the Hamiltonicity game, that was Krivelevic in 2011. And the perfect matching game, that just follows from the results for the Hamiltonicity game. Now for the triangle game, this threshold bias is not known, like the correct constant isn't known. We know that the threshold bias for just the triangle game is of the order of square root of n. And there already Fratal and Erdős proved 2 bounds that were a factor of 2 or square root of 2 apart. And then these bounds were, one of the bounds was improved by Balogh and Samoti, and then very recently by Galazic and Srivastava. But it's a smaller and smaller constant, but we still don't know what's the exact constant. Now, if you look at these threshold biases for these spanning games, then you may find that this value looks familiar. and the familiarity is brought into context like that. So let's consider a corresponding random game. So you replace maker by a random maker and breaker by a random breaker. So both of these players, they just pick their edges uniformly at random from whatever is not claimed yet. So in some round I, maker picks a random edge from all the edges that are not claimed yet, and then breaker picks B, random breaker picks B edges uniformly at random from all the edges that are yet unclaimed. And what will happen is that at the end of the game, the distribution of the graph of this random maker looks like G and M, like the random graph with M edges drawn uniformly at random, where M is a 1 over B plus 1 proportion of all the possible edges. So in this random game, of course, we can't prove that for sure random maker wins, but we can prove that if your bias is less than, say, 1 minus epsilon n over log n, then with high probability, the corresponding random graph is connected. And if your B is larger than 1 plus epsilon times n over log n, then with higher probability, the corresponding random graph is disconnected. So it turns out that the threshold bias in the random game, when you have two completely random players, this probabilistic threshold is the same, asymptotically the same, as the one when you have two clever players. And that's true for all of these three spanning games. And that's maybe why the results that I showed previously, the one due to Gibber and Sabon by Krivellevich, was such a big deal because they proved that asymptotically these two threshold biases are equal. And well, for the triangle game, this is not the threshold bias in the random game and the threshold bias in the clever game. They do not coincide, not even in the exponent of n. And generally, it is not very well understood when does the clever game or when does the random game give you a good intuition for the clever game. And that intuition is called the random graph intuition or the Erdős paradigm after Erdős. Okay, so the question is when does completely randomness, playing completely at random, is just as good as playing when both players play cleverly. And we don't know a general criterion for that. And well, in one of or like determining which games satisfy this random graph intuition is one of the big open questions in the field of positional games. So there are some results that somehow connect directly a random game with a clever game. And the first contextualization of such a connection is due to Bednarska and Wojciech from 2000. So they considered the H game. In the H game, the goal of maker is to obtain a copy of some fixed graph H. So that's like generalizing the triangle game. So before we saw the triangle, no matter where, you don't care where in your graph you see this triangle, but you just want a copy of a triangle. In the H game, you just want a copy of your graph H, some fixed small graph H, and you wonder, what's the threshold bias for this game? And they proved that this threshold bias is of the order n to the 1 over m2 of H, where m2 of H is the 2 density. We've written down the definition down there. It's a parameter depending on H. And well, the upper bound, as I said earlier, that's always a strategy for breaker. But what was really striking was their strategy for maker. So for the lower bound, you have to give for bias of the order c times small c times n to the 1 over m2 of H, you have to give a strategy that is a winning strategy for maker. So that maker at the end of a game occupies a copy of H. Now, what's their strategy? And the strategy is that maker plays at random, completely at random, as if breaker didn't exist. So in every round, she's only concerned with her own edges, and she chooses an edge uniformly at random from everything that maker doesn't occupy. Okay? And so if maker could claim all of these edges, then maker's graph would have a distribution of random graph GNM. Now, sometimes these uniform edges will hit edges that are already occupied by breaker. But what they proved is that most of these edges, at least for the first large part of it, almost all of these edges hit an unclaimed edge. So in fact, what they proved is that for this GNM, that maker can occupy a subgraph of GNM which has almost all of its edges. So 1 minus epsilon proportion of M. Okay, and then they proved that, well, if your B is of the order small constant times n to the 1 over m2 of h, then your GNM has the property that no matter which epsilon proportion of edges you delete, in the remaining subgraph, you will definitely find a copy of H. Okay, so it's a random strategy, which of course doesn't always work. Like the random strategy might give you a stupid subgraph with small probability, but it is a winning strategy with positive probability. So with positive probability, this strategy will get you a copy of H. Now, why does that mean that maker has a winning strategy? Well, if breaker would have a winning strategy, then breaker would always win, no matter what maker does. So having a random strategy and that is a winning strategy with positive probability is enough to show the existence of a winning strategy, even though you have no idea what this strategy, the explicit or deterministic strategy, would look like. So they used this robustness result, and that worked for the H game, but this type of just doing things completely at random does not work for when your winning strategy is spanning. So when you have some graph H that is like hitting every vertex, then the count and you do this random strategy, then breaker strategy would just be to play at one vertex only, and then it would be very unlikely for maker to hit this vertex before breaker isolates it. So this sort of strategy does not work when you have a spanning structure. And then the next result in this line is due to Faber-Krivelevich and Naves, who turned this global robustness or global resilience result into a local resilience result. So what's their strategy? They say that, well, for every strategy of breaker, whatever breaker is trying to do, maker just draws a random graph. And if your a random graph TNP, and if your P is at least a constant times log n over n, and at most a small constant times 1 over b, then with high probability, this random graph is such that maker can claim a subgraph of GNP, so that at every vertex, you have at least a 1 minus epsilon proportion of the expected degree. So this strategy works for any kind of property when GNP is locally resilient for this property. So GNP has, for example, a perfect, for example, when B is C times n over log n, then the corresponding GNM has the property that it does contain a perfect matching, but even more, even if you allow to delete any epsilon proportion at every vertex, the resulting subgraph will still have a perfect matching. So they reproved the earlier results on the order of magnitude of the threshold bias, but with a suboptimal constant. But the point was to really make this direct connection to playing randomly. Okay, But this strategy also has shortcomings. And one of the shortcomings is that this strategy will not work if the property you're trying to achieve is not locally resilient. And remember that we are going for a clique-factor when every vertex is in a triangle. Okay, so this kind of strategy simply won't work because because at a fixed vertex you could delete all triangles that this vertex is in by just deleting a small proportion of the edges incident to this vertex. Right, and overcoming this shortcoming, there's a result due to Allen, Böttcher, Kohayakawa, Naves and Person that appeared on the archive in 2017. I don't think it's published yet. So they proved the following theorem, and that looks a little bit technical, but let me talk you through it. So the theorem is as follows. You're given n and epsilon, and think of epsilon as being just a small constant. So if you take your p at least 1 over root n times some huge constant, and it's at the same time it should be at most 1 over b times some other small constant, right? So then the theorem says that Maker has a strategy to claim a subgraph of G and P with the following properties. For once, at every vertex, you have at least the 1 minus epsilon proportion of the edges incident to this vertex. And in the neighborhood, you get at least a 1 minus epsilon proportion times the expected number of edges in the neighborhood. So in G and P, you have that the degrees are concentrated around NP, and the edges in the neighborhoods are concentrated around P cubed net squared over 2. And then this says that Maker has a strategy to get a subgraph which is very close to it. And the strength of this theorem is that you can apply it with an epsilon tending to 0 with n, but then you sacrifice p. So then p needs to be significantly larger than 1 over root n, and also significantly smaller than 1 over b. So you get a sparser random graph, but you get much more close to being an actual subgraph of the random graph. Okay, now let's see what this theorem is useful for. So they proved in the same paper the following corollary, that if I want to get a copy of a graph H, but now H is allowed to be spanning, to occupy all n vertices, but what I require from H is that the degree is bounded by some d. Okay, and in that game, Maker has a winning strategy if the bias b is at most the c times n over log n raised to the 1 over d. Okay, so and the proof is really just this, like apply the previous theorem. So you have the strategy to get the subgraph of a G and P, and then you use a sparse blow-up lemma to show that such a subgraph contains all bounded degree spanning graphs. Okay, so what I just said is actually something stronger than what I've written. Namely, they actually prove a universal result. So for that bias, Maker has a strategy so that her graph contains all of these graphs H simultaneously. Right? That's stronger than just saying one graph H with bounded degree D. And I should also say that they proved a more general version where the 1 over D, do you see my mouse, Alex? Yeah, okay. So there's you have this more general version where you replace this bound 1 over D in the exponent by something depending only on the degeneracy, and the bounded degree goes in the multiplicative constant. So that's something, oops, that's more general. Good. Now let's look at 2 specific examples. So one specific example, and now we are at our clique factor. So if this d is 2, then the theorem says if my bias is at most an n over log n square raised to the power of 1/2, then maker wins the triangle factor game. So if your bias is that small, maker has a strategy that at the end her graph will contain a triangle factor. And that's quite amazing because we have seen that root n is just a bound for breaker, or 2 times root n is a bound for breaker to win the triangle game. So for b at least root n, to root n, breaker can prevent any single triangle in maker's graph. And if you go down a square root of log factor, then in fact, maker has a strategy to even claim a triangle factor. Okay, and the second example I will mention here is the K4 factor game. Now that says, let's just plug in d equals 3, then this example says that if b is at most n over log n raised to the 1/3, then maker has a strategy to win the K4 factor game. And in the same paper, they prove that for the K factor game, at least the n to the 1/3 is best possible. So up to the log factor, that's known. Now, why would you care about the K4 factor game? So, well, one thing is it's a natural extension of the perfect matching game. So if you think about the perfect matching, that's just a K2 factor. And so now here you just increase the sizes of these little cliques and you want disjoint union, vertex disjoint union of these cliques. Okay, but K4 is where that story ends. So here's the summary of what they do for the clique factor game in that paper. So that they show that this the bias is of the order n to the 1 over d plus some little of 1 in the exponent when d is 2 or 3. And they also say, well, probably the 1 over d is not correct when we go to larger d. So they already have some heuristic or some ideas why the 1 over d might not be correct. And remember that their result really gives something universal. So it's, you get, yeah. And that's what we confirm. So we prove that when your d is at least 3, then maker has a strategy in the b-biased maker-breaker game to win the k d+1 factor game if your bias b is at most c times n to the 2 over d+3. Okay. And this, our result really only works for d at least 3. Now for d equals 3, this exponent is exactly the same as the 1 over d in the earlier result, but for d at least 4 and larger, this exponent is strictly larger than the 1 over d. So it's larger than what they had for the triangle factor and the K4 factor. And then we also proved that that's the end of it. So breaker can win the clique factor game when b is at least a large constant times the same order of magnitude. Okay, so before I tell you what this exponent is, where it comes from, let's just fill out this table, which I had before. So we had these 3 spanning games, the connectivity game, the perfect matching, and the Hamiltonicity game, where the random threshold really is asymptotically equal to the clever threshold. And for the triangle game, this doesn't work. And for the triangle factor game, we have in the clever game, we have the threshold of n to the square root of n times some polylog factor. So we actually do not know what is the correct polylog factor. And then more generally, for larger d, we have the n to the 2 over d+3. And in the random graph, just for comparison, that's the celebrated result by Johansen, Kahn, and Wu. That's the threshold to obtain for GNP to contain a clique factor, a KD+1 factor. And here I should say these little of ones, they are they're different than this little one. So in the Yuans and Kanwu, you do know the exact polylogarithmic factor. You don't know the leading constant. But these little ones here, they are known. Okay, so what is this 2 over d plus 3? What's the intuition behind it? And to give you an intuition, I will give you a heuristic. So let's remember for these spanning games, the perfect matching, connectivity, and so on, the best that Böttcher could do was to completely isolate a vertex. And that turned out to be the correct size of threshold bias. And so here, Maker's goal is to obtain a clique factor. So in Maker's graph, every vertex will be in a copy of KD plus 1. And let's try to mess with just that. So let's try to find out for which B can Böttcher achieve that there exists some vertex V, which is not in a copy of KD plus 1. That's all we want. So then certainly Maker's graph won't contain a KD plus 1 factor. And what can we do? Well, we fix a vertex V, and then Böttcher's strategy will be to just play edges incident at V. And so at the end of the game, Maker's degree of this vertex will definitely be at most n over B. Okay? And now all we need to do, let's assume for a second that Maker is in favor for us and only plays at V. And so we know exactly what is the neighborhood in Maker's graph. And then in this neighborhood, we have to make sure that there won't be a copy of a KD. So if we can obtain that, then this vertex V will not be in a copy of KD plus 1. And we do have a criterion for how to prevent a copy of KD on some K n over B, which is due to Bednarska-Woodchuck. So that's the theorem I showed a couple of slides earlier, which tells you if your B is at least some constant times the size of the board raised to 1 over the M2 density of this KD, then Böttcher has a strategy to prevent a copy of KD in this board of size n over B. Actually, the number of vertices is n over B. And if you rewrite this, then that just translates to B being at least some other constant times n to the 1 over 1 plus the 2 density of KD, which is exactly the bound that we got. So that's the right intuition to give you the right threshold bias. And so that's just heuristic, right? Because Maker can do anything. Like Maker could play at this vertex V or could play outside. And what you have to do, you have to dig into the strategy of Bednarska-Woodchuck. It's a potential function technique for those who know positional games. And you have to figure out that, in fact, you can adjust this potential function technique to this dynamic setting. And the only other thing I'll say at this point is that we really need that Maker's bias is 1. So in one round, Maker either increases the size of the neighborhood or Maker plays inside the current neighborhood. So that's somewhat crucial. But that's where I leave Böttcher's strategy. The much more interesting part is Maker's strategy. And that is even interesting if you're not too much into Maker-Böttcher games, because that it will be a question about how do I find a clique factor in pseudorandom graphs. So before I tell you how to find a clique factor in a pseudorandom graph, I'll tell you how Maker can build a pseudorandom graph. And by pseudorandom, I mean these 3 properties, and by no means I expect you to read them right now. But these are the properties, and rather than walking you through these properties, I will tell you how Maker will achieve these properties. And then I'll come back to the properties. So what is Maker doing? For once, we are using the earlier result by Böttcher, Kohayakawa, Naves and Person. And we use a strategy which says that Maker has the theorem which says that Maker has a strategy to get a subgraph of G and P, where P is a small constant times the inverse of the bias. And here epsilon is really a small constant, but tiny constant. And you get a subgraph of G and P, and you get epsilon close to the expected degree, and you get epsilon close to the expected number of edges in every neighborhood. Okay, so if you do that, that's great. So then you satisfy the first two of these properties. So these you can directly get from that theorem. And now let me tell you what these first two properties are. So the first one is just that your minimum degree is at least like some proportion of the expectation of n times p. And the other one is just between any two sets. One has linear size and the other one isn't too small. You find a vertex which has the right proportion into this bigger set. So both of these standard pseudorandom properties. And then this P2 is as follows. So in order to find a clique factor, I better make sure that for every vertex, if I look at its neighborhood, I find a copy of KD in this neighborhood. And this P2 tells you something stronger. It tells you that every smallish subset of the neighborhood contains a KD. So you want to have some room to wiggle where you embed your KD. And to prove that, we're using the KLR conjecture, or the proved KLR conjecture. Yeah, which is now proved. Right, but that GNP won't be good enough, or rather the sub won't be good enough to get the third property. And for the third property, we really need this stronger version of this theorem. So we apply the same theorem, and here I just replaced the epsilons with gammas and the p's with q's. And you get a second graph, and you just take the union of those two. The second graph is a subgraph of a G and Q. And now your Q is much smaller, like by a power of n smaller than your P. But you get, and yeah, gamma is like a power of 1 over n. And so you get a subgraph of G and Q, but you're much closer to this G and Q, to the actual random graph. And Q is still big enough to get this P3 property. And what's P3? P3 is that if I take any d+2 sets of size at least n to the 1 minus beta, so not linear, but like sublinear, then I find a copy of this graph, which is like a k d+2. So it's like 2 k d+1s that intersect on a kd. Okay, so it's a copy of a complete graph of d+2 vertices minus this edge going from the first to the last vertex. And I find this copy with one vertex in each of these sets. So yeah, that's all I want to say. How Maker obtain such a pseudorandom graph. So using both of these strategies, the theorem in both forms. And then you get what we call here a certain pseudorandom graph. Now, why does such a pseudorandom graph contain a clique factor? And this is where this P3 comes in, right? So we're using this P3, and this is really, okay, I should say about the strategy, that this goes back initially to ideas due to Krivellevich when he found triangle factors in pseudorandom graphs in 1997. And Raiko used this, but like developed this much further to prove the clique factor, the existence of the clique factor in pseudorandom graphs, which are nearly with an optimal second eigenvalue, or nearly optimal second eigenvalue. So this is where this strategy comes from. So we're using this P3 to find long chains of these KD D plus, or let me say KRs for D+1, so KRs, and they're glued together at these endpoints. So we find these chains, and these chains, they can be quite long. So how do we find these chains we're using on the one hand is P3, and the other thing we're using is a depth first search argument. Like as if you find a long path in a connected graph, like this is like finding a long chain. When you know that between any two sort of large subsets, you find this such a subgraph. So we find this chain of length n to the 1 minus beta. And what's so special about this chain? So if I take one of these green vertices, one of these gluing vertices, and I take it out, then the rest of the chain falls into copies of Kr. So removing exactly one vertex leaves this chain with the Kr factor. And now I do not just find one chain, but I find many of these chains. Okay, so I find lots of these chains, doing the same argument again. And once I have like R or D plus one of these chains, then because I have enough of these green vertices in every one chain, so I have at least n to the 1 minus beta in each of these chains, then I know that between these green vertices here and these green vertices here and here, I find a copy of Kr that has one vertex in each of these layers. And once I find this Kr or Kd plus 1, so I'm taking away from each chain one of these vertices. These orange vertices form a copy of K4 in this case, and the remaining chains, they also separately fall into vertex-disjoint copies of Kr. So that's really good. So if I could just find these chains and cover my whole graph, then I would be done. But I can only do this as long as there's like there are vertices left to play with. So instead, I find batches of these chains. So in my first batch, I do not just find R of these chains or D plus 1 of these chains, but instead I find N to the beta of these chains. And they together occupy a tiny proportion of the full graph. So I'm omitting constants now. So they cover maybe some small epsilon times n vertices. And then I keep going, and I can't find the long chains anymore. They will be shorter, but I find longer ones. And they will have a special property that I'll come back to in a second, but I just keep going. And after a constant number of these batches, what I find is chains of length 0, which are just vertices. So they're just the green dots without any KD plus 1s attached to them. But there are epsilon n many of those. So I find a constant size subset of these chains of length 0. Now that's not so special. But what's special is that these batches of chains are connected through an upward absorbing property. Okay, so I'm not telling you how you find these chains, but you have the property that if I'm in a certain level and I take any subset of chains, so these are the yellow chains here, then for these ones I can find green chains in the layer above so that the union contains a Kr factor. That's the upward absorbing property. And this holds for every of these consecutive layers. So in particular, from C0, I can take away an arbitrary subset of vertices. And this property will tell me that in the layer above, for this subset, I find chains that together with this subset form a Kr factor. And then I just continue and go up layer by layer until I'm at the very last layer. And here I have that the chains are long enough. And so whatever is left, if it's a multiple of R, I find my copies of Kr that go across, and everything falls into a Kr factor. So what we have built in this way, and that's the last picture for this proof, is an absorber. So here you see these long chains and the shorter chains going all the way down to C0, which is this set of size epsilon n. And this set A, all of these chains together, has the following absorbing property, that whatever subset of C0 I'm taking away, in the remainder of C0, together with all of these chains, I definitely find my KD plus 1 factor. So now what's my strategy? I somehow use these other pseudorandom properties to cover the rest somewhat greedily with copies of KD plus 1 in a way so that, well, I won't be able to cover everything perfectly, but in a way so that the remaining vertices that I can't cover have a good neighborhood inside this C0, which is linear size. And so I find then for each of these vertices, KRs that contain these vertices, and I'm using some subset of C0, I don't know which one, but whatever subset I'm taking in the remainder, I can like absorb the rest of C0 into these chains and find a KR factor. So that's really all I want to say about this strategy. So let me finish with some conjectures and problems. So the first, our conjectures that this is actually getting the KD plus 1 factor is the hardest for Maker. So if you have some small constant times the same, like n to the 2 over d plus 3, if that's your bias, then in fact you can get any other graph H on n vertices with a maximum degree at most d. And that follows us two other conjectures from extremal combinatorics and from the random graph theory. So for example, we've seen the Johannes and Kahn-Wu telling you the threshold bias for GNP to contain a KR factor. And the conjecture there is that this is actually the threshold bias for all other graphs of bounded degree D. Okay, and then a problem which is generally mentioned is that these strategies for Maker, they rely on this random exposure of edges, and they only give you a winning strategy, a random strategy that wins with positive probability, and that only gives you a theoretical existence result of a deterministic strategy, but no one knows how this looks like. So can you find an explicit winning strategy for the H game, for the Hamiltonicity game, or for the clique-factor game? And finally, I mentioned this before, is that our bias, the strategy for breaker really depends on Maker being able to only claim one edge per round. So what happens if you allow Maker to claim 2 edges per round? I don't know. And that's where I finish. Thank you.
Great. Thank you, Anita, for a great talk. If you have any questions, then please signal in the chat and we'll unmute you. So actually, I have one question. So you have this, so the conjecture you have at the top here, that if you have maximal degree D, then it's worst for KD plus 1 factor. Is this easier if, so if you fix just a fixed size H and ask for an H factor? So does your proof strategy then work? And because you could chain these things together again through copies of a vertex.
Yeah, but if so one thing I really don't know, if this H has a vertex of degree 1, then I wouldn't know what's the correct so if your H has maximum degree D,
yeah,
but is in the subgraph of KD plus 1, then I don't know, because yeah, I simply don't know. I know that breaker strategy won't work, but yeah, it's possible that some version of this of the proof will go through.
Okay. Do we have any other questions? Okay. So well, let me thank Anita again for a great talk. And now I will attempt to unmute everyone and see if we can overwhelm Zoom with applause. Oops. This will take me a minute while I figure out how to, there we go.